Okay, let's start. We are very happy to have Yotam Dikstein here. He did his PhD at Weizmann with Iris Dinur. Now he's a postdoc at the IAS. He's one of the leading figures in the study of high-dimensional expanders and other high-dimensional combinatorial objects, which I'm sure he will very soon tell us about.
Right. Yeah, so thank you for having me here today. Today I'm going to tell you about high-dimensional expanders. These are basically the hypergraph analog of expander graphs. And in recent years, they got a lot of attention, I think, because people use them to solve a lot of interesting problems in complexity mainly. I kind of hope that by the end of this talk, we know what a high-dimensional expander is, why people think it's so interesting, and we'll also see some applications. Good. But before I tell you about high-dimensional expanders, let's talk about just expander graphs, which are a more basic object. Yeah, no? Okay.
It's the generic.
No, I think, okay. Right. Good. No, now it works.
Yeah.
Great. Let's start with talking about expander graphs. Basically, expander graphs are graphs that are very well connected in the following sense. If you take an expander graph and you try to cut its vertices into two disjoint parts, there will be many edges that cross the cut, no matter how you try. So I put kind of the formal definition here just for regular graphs. Of course, you can generalize to arbitrary graphs. So we say that a regular graph G is an eta expander, where eta is some parameter, if for any set of the vertices, the number of edges crossing the cut between S and its complement is at least eta times the smaller side of the cut. And so it models well connectivity. If a graph is just connected, then there will be always at least one edge crossing the cut. In an expander, we want many edges. And kind of, even if you haven't seen this before, already kind of let me tell you that there is some tension hiding in the definition, at least when the regularity is very small, like 4 or 5, and the number of vertices is huge. Because on the one hand, in a regular graph, the graph is always kind of edge sparse. The number of edges is linear to the number of vertices. But on the other hand, expansion really sounds like something that that inherently only dense graphs should satisfy, that there are sort of many possible cuts that you can take, and you want many edges crossing every cut. And so maybe the first way you think is that this should imply that many edges should be in the graph in general. However, this is not necessarily the case. And actually, we know that very sparse expanders exist. So for any eta here that you want, you can find a large enough but constant regularity parameter D, and families of D-regular graphs, or graphs where every vertex has degree exactly D, and that are eta expanders. This has been known for actually many, many years. And of course, this is not the only definition of expansion. There are actually many definitions that are classical in the literature. I gave you the definition that's called edge expansion. There is also another definition that talks about eigenvectors or eigenvalues of the adjacency matrix of the graph. Other definitions that talk about random walks. I won't give them here today, but it turns out that all these definitions, and there are even more I did not mention, they're actually equivalent to one another, at least qualitatively. Kind of you satisfy one if and only if you satisfy them all. And this is to say that sort of well connectivity or expansion is a property that is really expressed in very, very different ways. And maybe the other thing that I want to tell you about expanders is that they're actually extremely, extremely useful. So I come from theoretical computer science and combinatorics, and expanders have been used to solve a lot of different problems, some of which, by the way, don't even have the word graph in the problem description. For example, constructing error-correcting codes. But even if you're not from where I come from, expanders have been used in many, many different areas to do many different things. And kind of the idea behind this is that graphs are very useful ways to model problems that we often care about. And if you can somehow reduce your problem to a problem about connectivity on the graph, and this graph happens to be an expander, then you can say very, very strong properties on this, which often help you solve your problem. So this is maybe just about expanders, but today I want to talk about high-dimensional expanders, or the hypergraph version of expanders. And so let me first try and convince you that hypergraphs are maybe also a very natural thing that we can try to embed problems in. So here's one problem, the stat problem, or the Boolean satisfiability problem, where you have some formula, maybe it's in this kind of CNF form, where you have these ands, and between it you have ors of variables of their negation. And in fact, you can also draw this formula as a hypergraph in a very simple way. So for example, for every variable or its negation, you can put a vertex. And whenever you have this clause, which is an or of variables, you can sort of put a hyper edge on the literals here. So if I have like x or y are not z, I will put a hyper edge between x, y, and the negation of z. Now, of course, this looks very syntactical, but it turns out that actually, if you know something about connectivity here or expansion, you can say interesting things about satisfiability of these formulas, and we will see something in this form later in this talk. Maybe another example comes from the probability theory, where you want to maybe study distributions over points with like many data points. And you can also imagine this in hypergraph form. For example, you can take all the points in A, B, and C and just put them as points in your hypergraph. And whenever you have a triple in the support of your distribution, you can just draw a hyper edge between the points of the triple. Again, this is just syntactical, and you can also put weights here to not lose information and so on. But again, it turns out that connectivity properties of this hypergraph can tell you non-trivial things about tail bounds of these distributions and things like that. And we will see this maybe by the end of the talk. So I hope I convinced you that we can also look at hypergraphs as very useful objects. And so we can try to define expansion for hypergraphs, or what's known as high-dimensional expansion. And we saw, or at least I mentioned, that there are different definitions to expansion in graphs. And people try to kind of generalize these definitions to hypergraphs. And it turns out that while in graphs, these things are equivalent, at least in qualitative sense. In hypergraphs, they're actually not. There are hypergraphs that satisfy some of these and do not satisfy the others. And kind of every definition really gives you a different theory of a different flavor, and also different applications, different examples, and so on. So in fact, in different papers, people talk about high-dimensional expanders, and they give different definitions. But fortunately, sort of nowadays, we sort of converged on like maybe 2 or 3 kind of main definitions. I'm going to give you only the most popular one, which is usually known as local spectral expansion. I won't explain why this is a generalization of spectral expansion, because I haven't given the spectral definition of graph expanders. But we will see what the word local has to do here, and we will kind of discuss why it makes sense. So let me try and just define it now. I'm going to make my life easy. So I'm not going to define it for arbitrary hypergraphs. I'm only going to define it for hypergraphs that have vertices, edges or hyper edges of size 2, and triangles which are hyper edges that have 3 points. Okay, so it generalizes quite straightforwardly, but I thought it would make our life simpler. And so what does the word local have to do here? We say local because this definition has to deal with neighborhoods. So recall, if we just have a graph with vertices and edges, the neighborhood of a point U is just all the points W or vertices W that are adjacent to you or connected to you by an edge. In a hypergraph as so, we have a generalization of a neighborhood that is called a link. So a link of a point U, sometimes denoted by this X sub U, both consists of a neighborhood set, so all the vertices that are connected to you by an edge, and an edge set, I'll call it E of U, which are pairs that are connected to you by, or that fit together with you inside a triangle. And so this is a bunch of points and edges, so this is actually a graph. And I think it's maybe simplest to just see this in a picture. For example, if you see this red point here, you can kind of follow the definition and see that its link is this 5 cycle here with the blue points and the yellow edges. And if you look at maybe this red point, you see, these two disjoint paths. And in general, you can, for every vertex, you can draw a graph in hypergraphs that look like this. Yes.
So it's WX in E.
WX in, yeah, okay. So thank you for that question. I was kind of sweeping this under the rug, but usually when we think about these hypergraphs, we want that if a triangle exists, then all kind of pairs or all edges actually exist. So no, but yes, if you don't want to assume this, then you'd have to, in addition, assume that this is also an edge. So my real answer is don't worry about it. But yes. Good. So what is a local high dimensional expander? For a hypergraph like this, we say that it's an eta HDX if two things happen. First of all, if I just forget about the triangles and I just look at the graph, then the graph that I get is an eta expander. And second, if I look at every link or every kind of small graph neighborhood adjacent to a vertex, this will also be a small eta expander. So you get both a global guarantee of expansion and a bunch of local guarantees of expansion in kind of every link. And so just to give us one example we can think about, let's talk about the complete hypergraph, which is a high dimensional expander. So what's a complete hypergraph? You just take endpoints and you put all possible edges and triangles. Again, if you forget about the triangles and just look at the graph, you get a complete graph, which is a very good expander. And if you stare at the definition long enough, you see that a link here will actually also be a complete graph just on one vertex less. Because everybody is adjacent to this vertex U except itself, and all the triangles are there, so all the edges in the link will also be. And then this will be an eta expander for sort of this value of eta, which is roughly number of points divided by 2. So this will be this HDX for this value. Now, of course, you can say, okay, Yotam, this is maybe a very dense object, right? Everybody is connected to everybody else. But in fact, as in expander graphs, actually, we know that sparse high-dimensional expanders exist, where you have number of vertices that can tend to infinity, and the neighborhood size will be kind of constant independent of that. This is, by the way, a much harder theorem to prove. There are many things that are unknown as far as we know as constructions of HDXs, but we know how to construct them so that they are very sparse.
So if this example gives you n over 2, how do you get to 1?
Sorry, how do you get to what?
Sorry, to n or to something that is closer
to the number of vertices.
Number of vertices.
Right. So this sort of has to do with my definition of expansion, which can sort of never go above half because I define it by this edge expansion property. This is really sort of the best expander and high dimensional expander that you can
that makes sense.
that you can expect for this number of vertices. If you look at spectral definitions that talk about spectral gap and you normalize things appropriately, then kind of here you're supposed to get 1 or 0, depends how you look, and like you can go as close to that as you want in sparse.
Yeah, maybe the question, but what sense it's sparse, you don't put any restriction on T.
Right. That's a fair question. Just to simplify, again, you can either think about if you have a triangle, then all the edges need to be apparent, and then you have an inherent failure. Or if you don't want to think about that, and you really just want to think about the edges, then you need to sort of define the link so that you will only have an edge there if also the edge is in the graph, and then it kind of also follows. But never mind how it's phrased here, you can also bound the number of triangles by a constant. Good. One thing that I do want to answer, maybe this wasn't asked, but people are thinking about this, is why define it this way, right? Why does it make sense? Let me give 2 answers, kind of coming from different areas. First, is that when people talk about expander graphs, they often think about them as maybe sparsifications or approximations of the complete graph or the clique. And in the sense that it behaves like a complete graph in many ways, even though they're very sparse. And it turns out that in high-dimensional expanders, you get the same kind of type of analogies. So if you know something about Boolean function analysis, you have the same type of Fourier decomposition on HDXs as you have on the complete graph, and also some hypercontractivity phenomenon. If you know something about random walks, you can define sort of high-order random walks, or random walks on the triangles of the HDX, and these will kind of behave similarly in a spectral sense to what's going on in the complete graph. And there are many other group theoretical and topological invariants that are kind of similar between the two. I would say that the theory behind HDXs is something that I'm very interested in research. Of course, I'm not the only person, and there's a big community kind of studying these questions. So this is maybe one reason why to consider this definition. And another is kind of empirically, where this definition turns out to be very useful. This local guarantee turns out to play well with arguments about conditional probabilities and so on. And so you can see it in many applications, currently most of them in complexity and coding theory, hardness of approximations and PCP theory, hardness simplification, which I will talk about in about 2 or 3 slides, and also construction of error correcting codes, analyzing random walks, and really kind of this is a very partial list of references, and there are many, many more. So maybe to just end the intro part of this talk, and to say kind of, in my vision, the study of HDXs really focuses on these 3 sort of separate but intertwined areas. The 2 bottom ones, understanding the theory behind them, or what we can and cannot expect, and also kind of understanding how we can construct these objects. These are very important, and kind of the more we progress in them, the more sophisticated applications we can have. And of course, kind of the error will also goes the other way around sometimes. So I really think that these can be as an useful and interesting object of expander graphs once we kind of know more about it. Right, so today I will tell you about some applications to computational complexity, and also a bit about the theory you can expect with high-dimensional expanders. I'm also interested in constructions. If you want to talk to me about this maybe after the talk, we can, kind of out of the scope for today. Great. So kind of the first story that I want to tell you about is where high-dimensional expanders come inside hardness simplification. This is a very recent work. We just kind of submitted it to stock. It's joined with Max Hopkins, Russell Pagliazzo, and Tony Pitassi. And to talk about hardness amplification, let's talk first about maybe hardness or hard problems in general. Of course, most of you know P and NP, P problems or functions that we can compute in polynomial time or efficiently, and NP things that maybe we can only verify their solution in polynomial time. And of course, it's widely believed that these 2 are different classes. In fact, it's so widely believed that in a lot of applications, for example, in cryptography, we really want to use problems which we suspect that they are in NP, but not solvable efficiently, not in P. But often is the case that the type of hardness that you actually need for your applications is a much more stringent type of hardness. So one way to kind of formalize this is average case hardness, which gives you a very strong guarantee that kind of every efficient algorithm that you care about fails not just on one specific input, but really on most or sometimes all of the inputs. So let me try and kind of formalize this. So it's worst versus average case hardness. In this definition, in the background, there is always some complexity class of what we call efficient algorithms. So think about algorithms running in a certain amount of time, implementable in a certain hardware, and so on. And you also consider a specific function on n bits, which you want to sort of argue that it's hard for this class. So maybe the worst case or traditional type of hardness is just saying that the function is not in the class, or that for every efficient algorithm in the class, there is at least one input on which this algorithm says something different and it answers differently. But average case hardness, which I would call delta hardness, is a strengthening of this that says that for every efficient algorithm, not only one input makes it answer differently, but actually a delta fraction of the inputs it answers differently from S. So here I'm just using the uniform distribution, so it's just like counting the amount of input. You can of course generalize this to your favorite distribution, and maybe just to emphasize that maybe one algorithm errors on this set of inputs and another errors on another set, but kind of each of them has its error set of size, at least delta, relative size. And of course, the kind of delta can be anything here, but we really want delta to be this like 99% of 1 minus something tiny, which says that efficient algorithms are almost always wrong on our problem or to compute this function. So kind of any efficient algorithm you have, it cannot compute even something that's close to the function that maybe we care about. So this is kind of the picture that we really want. And of course, it's very natural to ask, do these hard functions exist for a specific complexity class? How do they look like? Can I describe them in a simple manner? And so on and so forth. And sort of hardness amplification is the theory that comes to sort of answer this. So in hardness amplification, you want to take a function that that it's maybe slightly hard, worst case hard, or 1% hard even, and to sort of turn it into another function that is sort of extremely hard, like 99.999%. And so maybe to give us a flavor, and also this will be the theorem that we generalize. So here's a theorem that's by Infaliazzo and Dikstein in the 890s, talking about amplification by repetition. Suppose I take a function f that's sort of mildly hard, 1% hard, and now I look at its repetition function. So this f prime that now doesn't get n bits of input, but it gets k instances of n bits of input, so k times n bits in total, and it outputs f on the first n bits, f on the second n bits, and so on and so forth. It turns out that this repetition will be sort of 99% hard. What I mean here is that for every epsilon, there is a sufficiently large k, such that if we repeat k times, we will get this 1 minus epsilon hardness. And of course, I should say already, maybe this looks very intuitive, right? Like I'm just asking you to compute f more times, so the hardness should accumulate. But there is a proof to do here. Like it's not a simple tail bound or something like that. There's something to do here. Anyway, kind of one caveat in this theorem is that this f prime, it's no longer just taking n bits of input. The input size is kind of really inflating towards this k. I will say, of course, also the output is growing, but kind of nowadays we know a lot of different ways to deal with output size, but input size is kind of a different story. Because this talk is already going to cover a lot of different things, I can't really kind of tell you kind of why this is important, but in fact, many applications rely on this k being small and even kind of as close to 1 as one can get. And even in a very extreme case, you can imagine that for certain classes, maybe if k here is too large, the algorithms really just can't read the whole input, so it even becomes somewhat trivial. But even outside of that, this is a very important problem. And maybe another point of view of this problem that kind of suggestively looks at hypergraphs is that f originally gets a single string of n bits, but f prime actually gets a set of strings. Of course, it gets a tuple, but kind of let's forget about that. And there are many, many more sets than single strings, and so this is why we kind of can't compress the input to stay at n bits. We really have to make it grow. And so you can ask, can I do the same type of repetition trick? Can I do the same type of hardness amplification, but by not growing this n by too much, just n plus kind of a very negligible overhead?
So the previous result, what was k in terms of epsilon, let's say?
Right. So it kind of depends on what kind of class you're trying to be hard against. But I think k can be kind of a polylogarithmic. Yeah, in 1 over epsilon. In 1 over epsilon.
Log 1 over epsilon, best.
Right, because if you're even guessing you will be correct in there. Right.
That's why we do the easy code. Most places, that's very easy answer. That's this down.
You have to start from, I guess you can reduce this 1% to something polynomial in.
Yeah, so you can reduce this 1%. You can start from worst case hardness, which is like 1/2 to the n with this technique. Then you need to kind of do something else to kind of get it to 1%, and then you can use repetition. Kind of it turns out that there's different flavors to problems of like how to go from worst case to mildness and from mildness to kind of this 99% hardness. Right. So I say that already Pagliazzo and Wigderson gave in their work some sort of de-randomization of this construction, or they managed to inflate the input to just a constant times n, regardless of this epsilon. But really, there has been no progress since then, at least not by this type of hardness amplification. And this is basically what we do in our theorem. We use HDXs to do exactly this. So the main theorem in this work is that for any n and epsilon, we have this kind of hardness simplification scheme where we take a function f and we amplify it to f prime, where the number of bits that f prime takes in is really n plus something negligible, which of course depends on epsilon, but rather mildly. I'm not writing, of course, all the technical things. I will kind of say that you can get the input and output lengths to be almost optimal in a certain sense, and that epsilon here can actually be kind of very subconstant. It doesn't need to be just a constant independent of n. It can actually grow quite nicely. And finally, I will say that in some applications, you also want this f prime to actually be efficiently computable if you do know how to compute f, if you kind of have Oracle access to it, or you're in a slightly stronger class. And so you also kind of get this very simply from our construction. And kind of just the gist of this is that, again, f prime, recall that it actually takes a set of inputs. And so what we do is we say, okay, let's not take all sets as possible inputs to this f prime. Let's only take kind of sets or hyper edges that come from a high dimensional expander, which has much less hyper edges, and therefore we can kind of compress the input. So kind of we start with some carefully chosen high dimensional expander with vertex set, which is like 0, 1 to the n, and hyper edges of size k. But we don't have kind of too much of them, so that we can really encode them using not much more than n bits. Yeah.
Is there a sense in which this is like better than what a probabilistic argument would give you?
What do you mean a probabilistic argument?
So like a probabilistic method type argument. There is a, if you just sample the sets in a
right. So at least the way we know how to prove the theorem, you cannot use a random hypergraph. You need kind of very well, you need like a lot of connectivity, both in a local sense and kind of connectivity of these like sparsified Johnson graphs, which I might say a word about. This is not to say that a random hypergraph cannot work for different reasons. It's just that I don't know how to. But I will say that kind of here you also need to say something about efficiency, because this is kind of proven in a way of reduction. You say, you know, suppose f prime can be computed efficiency, and then f can, and kind of random hypergraphs, they don't have a lot of structure kind of inherently, right? So you'd have a hard time arguing about algorithms there. In any case, our theorem just said that if you really kind of sparsify the input space of f prime to just the hyper edges of the HDX, you will still get hardness. Good. I want to say something about a corollary, a very neat corollary we have on error correcting codes. I don't expect everybody to know error correcting code, so let me just kind of hand wave. An error correcting code is a way to encode n-bit strings into longer strings in a way that works well with decoding under noise. So suppose that somebody took some encoding and flipped some of the bits to get sort of a noisy version of it. In an error correcting code, we also have a decoder that can kind of, we can read back the string that we encoded, even though some of the bits were flipped. And of course, you know, traditional theory of error correcting codes, it cares both about the rate, which is kind of the blowup you get from your original string to the encoded string, and the decoding radius, which kind of asks how many errors can the decoder handle in order to get, still get kind of the original string back. And so we are, of course, from computer science, even from theoretical computer science. So we do somewhat care also about efficiency of a decoder. And one way to talk about efficiency is this question about local decoding. In local decoding, you're in a scenario where you don't really want to decode the whole string that was encoded, but you only want to see very few bits of it. So you should maybe think about, maybe you're a big company like Amazon or Facebook, and you encode your whole user database because you want it to be resilient to storage faults and whatnot. But now, if somebody wants to query this database, they don't deserve to really decode a huge database, right? They only want to look at one row or just a few bits about the user. So kind of local decoding is something that sort of helps us do like small decoding without reading all of the huge code work. And so a challenge that has been apparent is to find locally decodable codes that have constant rate, decoding radius that is very near half the bits, where kind of half is optimal informational theoretically, and also that you really read a tiny fraction of the bits. I'm not going to say what's tiny because it's a formula, but kind of you should think about something that's like a smaller growth than any polynomial. And this is basically a corollary from our previous theorem. We show that for any epsilon, there are locally decodable codes like this with constant rate, decoding radius that's almost half, and they really read a tiny number of, okay, there's some lag, I'm sorry. They really read a tiny number of bits. And in fact, they're also very efficient. You can kind of encode and decode in like quasi-linear time, and they're very parallelizable. And kind of they're really interesting in that sense. I will say I call this a corollary because it actually follows a very nice observation by Dan, Trevisan, and Vadhan that shows that if you have a code with kind of a modest decoding radius, you can sort of use any hardness amplification theorem that you have to kind of amplify it to a very large decoding radius. So we're kind of getting this almost for free using codes from the literature by Koparty et al. And kind of the fact that we have a small block in the input side sort of corresponds to the fact that we're not ruining rate too much.
So what is this tiny number of bits?
Right. So it's the number of queries you need for this code times some log factors, which is like exponential in square root log n log log something like quasi-polynomial. It's not polylogarithmic though, which could really be nice. But I would say that kind of you can also kind of view this theorem as like a very general way to amplify. And if you get a better code for like the small noise regime, then you can amplify them to get essentially up to polylogarithmic factors, the same query complexity and higher ones. Yeah. Okay, what lies in the proof? I'm not going to say anything really about the proof. I do only want to maybe give some slight intuition about why HDXs are the correct tool here. But don't worry if you're not following this too much. Like in 2 minutes, we'll talk about something else. Recall that we have an HDX, and in HDXs, remember that we both have a global kind of guarantee of expansion, and like in every neighborhood, we have these local guarantees of like expanding graphs. And in our proof, we also analyze a global object and many kind of tiny local objects, and we need expansion in both of them. So kind of the global graph is a graph where it's kind of derived from this hypergraph, where you actually take the points to be the hyper edges, and sort of the edges are pairs of hyper edges that intersect on a lot of vertices. So kind of in a K hyper edge, you want at least like square root K intersection. And kind of the thing that we really use about this hypergraph is that you can kind of efficiently find short paths in it. So kind of for every pair of hyper edges, you can kind of find a short path of hyper edges in this graph, namely, a bunch of hyper edges where every two kind of intersect sequentially in a lot of vertices, and you use this for some kind of belief propagation. But I will also say that this can also be found efficiently, at least in some high-dimensional expanders that are kind of carefully chosen. So kind of the effort here is not to prove the existence, it's really kind of to construct these by hand, and there's actually a nice algorithm behind this. And the second thing is sort of a local graph. Kind of for every hyper edge S0, you look at a bipartite graph where on one side you just put the points inside S0, and on the other side you put sort of the neighborhood of S0 in the global graph, or all other sets that kind of intersect S0, and you connect a point to a set if one is contained in the other. The definition itself is not super important. The important thing to understand here is that kind of we're looking at the global graph, and we're kind of deriving local graphs using neighborhoods of this global graph. So at least syntactically, this may sound kind of reminiscent of this definition of an HDX, where you kind of also have some kind of neighborhood guarantee. And so the property you really need here is expansion, and you sort of use the expansion of links in the HDX that you use to kind of argue about the expansion in these things. So at least this maybe gives you a flavor of why global and local kind of appears here. Maybe it's a good place to pause for questions, because I'm going to go to something else now. There are.
Is this where you the difference from random
in both, actually. Like first of all, in this.
This I'm finding the pattern.
Yes. And also in these graphs, if you take a random hypergraph that's like in the right density for this theorem, then this type of graph would not even be connected. Like most hyper edges won't intersect on more than like constant number of vertices with others. So we actually are using it in both places. Oh, sorry. Good. Now we're going to say things in a much higher level. Good. So now I'm going to talk about hardness of approximation. This is a line of works. The first two with Irit Noor appeared in Stock 2024, and the last with Irit and Alex Fox of the same year. And he talks about hardness of approximation. So what's hardness of approximation? Let me just kind of tell you by example. So suppose we look at the three-set problem, where we kind of get a formula in the CNF form, and maybe we want to understand or even find an assignment that satisfies it, or at least see if there exists such an assignment. Of course, this is an NP-hard problem, so we can think about maybe trying to approximate. So one way to think about approximations here is maybe I want an assignment that doesn't satisfy all these clauses, all these ORs, but maybe 90% of them or 80% of them or something like that. And so here's one very kind of silly algorithm, just guess. So you get a formula, and for every variable, you just flip a coin to decide whether it's true or false. It's not too hard to kind of compute that in expectation, you will actually satisfy about 7/8 of the clauses, so about 87%. So this kind of gives you, an 87% approximation guarantee, at least in expectation. And you might imagine that, if you do something more sophisticated, you kind of look at the formula and think about it a bit, you might be able to do something better, but actually you can't, at least not in the worst case and not efficiently. So for any constant epsilon, if you want to get 7/8 plus epsilon assignment that satisfies this fraction of the clauses, you cannot do it in polynomial time unless p is equal to np. Even if the formula is actually satisfiable, you cannot beat the 7/8 in polynomial time. And I find this very satisfying, right? Like doing 7/8, I can do without looking at the input actually, and doing anything better, I cannot do efficiently. And this is not the only such problem where we have these very nice results. And kind of you can ask, how do you prove such a result? I will only kind of give you one component in the proof, which is Ran-Raz's parallel repetition theorem. And it says the following. Suppose you have a such formula where you know that there exists an assignment that actually satisfies all the clauses, that completely satisfies it. But in polynomial time, you somehow cannot find a formula that satisfies more than 99.9%, so just like a small gap. Raz's parallel repetition theorem is actually a reduction that gives you back another formula which again, it is completely satisfiable, but in polynomial time, you cannot find an assignment that satisfies even more than 1% of the clauses. This is not a three-set formula, okay? The formula looks like something else, assignments look like something else, but still kind of it amplifies the gap of what's possible and what's possible in polynomial time proficiently. And kind of what is this set star? I won't say too much, but kind of if you look at the original instance of phi in, which has these bunch of variables, then like the psi out, the thing that you get from this reduction will have, a new variable for say every set of kind of 100 old variables. So it will be indexed like this. So I hope already you kind of recognize this picture. In the clauses, you get something similar. You also take a bunch of clauses and construct a new clause from them, and so on. And so this is also some kind of amplification by repetition. But this time it's like amplifying the gap of what you can do efficiently by some type of repetition. And again, the same caveat holds, right? Like the number of variables or the length of this new thing, it blows up from n to, to some large polynomial in n, kind of increases the more we kind of want to repeat or the more we want to increase the gap. And really, we want to keep these things kind of well-tamed or well-behaved. I mean, maybe one motivation is that sometimes we want this to maybe be super constant, and in many applications, this actually comes up. And so you can ask, is this blow-up actually necessary? Or maybe we can, maybe we can sparsify these variables and clauses kind of using an HDX. And here, the answer is again, yes. And I will kind of say that the answer is much more complex here. So the answer is yes, you can do this repetition without blowing up the number of variables. To do this, you kind of need to look at your formula, and you kind of need to kind of massage it and kind of embed it inside an HDX. This is not the work that we did. This is actually very recent by Bafna, Do Minzer, who's here, and Vias. And they kind of showed a very non-trivial way of how you can take any formula and kind of embed it in an HDX. Let me kind of just handwave that when I say embed it in an HDX, kind of recall we have more of a hypergraph point of view of formulas sometimes, and we can kind of change them a bit so that you get an HDX. And then once you have an HDX, you can kind of do this gap amplification, which is really all these works. Where once you kind of start with something that already lives on an HDX, you can actually do this parallel repetition where the number of variables kind of stays the same. I will say that we're not the only people that kind of were interested in this. Bafna and Minzer and Bafna, Lifshitz and Minzer also have works that that kind of study the same problem and get really a very, very similar result. And I kind of even will say less about the proof here. Maybe just that, in fact, the HDX that we kind of get here or kind of have to use is not just the definition that I gave in the beginning of the talk that talked about like this plane expansion. It really had more also, in addition to that, also more of an algebraic topology flavor to it. And this is not just an artifact of the proof. Like you actually need to say something about the topology of the hypergraph in order to get this parallel repetition. And kind of the final work in the line of works that I discussed really kind of construct these topological HDXs using sort of group theoretic tools. Great.
Let's show this gap amplification. Does it have implications to hardness of representation? Part that you amplified it. As far as I understood, right, took a problem, amplified the gap, and reduced it to a different problem, right?
Right.
So,
of course.
What does it imply in terms of hardness of representation?
Yeah, so that's a great question. Once you know how to do these two steps, so especially in this work by Bafna, Minzer, and Vias, you show that using this gap amplification together with this like this embedding thing, you can actually construct PCPs with like a very good soundness guarantee that also have very succinct proofs that are like n times some polylog. And kind of previously, you knew how to do this only for like a very small soundness gap, because you didn't know how to do this parallel repetition thing without kind of blowing up the instance. And this in turn has, it has amplifications of gap problems of many other sort of parts of approximation. Good. So I have maybe 5 more minutes. So let me just tell you a bit about some theory building in HDXs. So this is the work with Matt Hopkins in Fox 2024 about Chernoff bounds coming from HDXs. What's a Chernoff bound? Imagine we flip 100 coins. How much will come up heads? Well, if it's a fair coin, then we really we know that in expectation it would be 50. But more than expectation, right? We don't think that either 100 will come up heads or 0. We really think that about 50 will come up. For example, what is the probability that more than 70 will come up heads? Okay, it's this tiny number that I took from ChatGPT, but I verified it myself. But it's really tiny. We really think that about 50 will come out. And so the one, at least theoretical justification of this is just the Chernoff inequality, which one way to phrase it is that if I have a function f on a probability space, say heads or tails or whatnot, with some expectation mu, and then I take k independent samples of this probability space, k coin flips, say, then the empirical mean will be close to the expectation with high probability. So empirical mean is just fancy words for take all f on the samples that we took and do an average on them. And so we can assess this mu with very high probability using this empirical average. So kind of slogan way to say it is independent random variables rapidly converge to expectation. Of course, this is a very basic inequality, lots of applications in theoretical computer science, in combinatorics, and in fact in statistics and science, right? We use this fact when we actually conduct experiments. And you can ask, what happens if our random variables are actually dependent? And, this comes up in practice, right? Like, I don't know, if you're learning something or, we often like to pretend that data that we see in real life is independent, but this is not necessarily the case. So kind of there is a very long answer to this question called concentration of measure, which is some kind of theory that exactly asks when I get this like nice convergence to expectation. And we know many examples. For example, sampling without repetition, or maybe closer to our world, sort of sampling using long walks in expander graphs. You can find many different distributions that exhibit the same type of Chernoff inequality. And these have, many important applications in de-randomization and so on. I don't know, what about high-dimensional expanders? So, what about them? HDXs are hypergraphs. Here we're talking about distributions. But as I said before, you can look at the hypergraph point of view of every distribution. If you look at the distribution over a set of inside a product space, you can model a hypergraph where the hyperedges are the support of this distribution. And you can ask what happens if this hypergraph, I know some connectivity properties of it. For example, if your distribution here is actually sampling things independently, so it's actually the product distribution, you will get the complete hypergraph from this. So at least in essence, you see that we have one example, which is the complete hypergraph where the corresponding distribution has Chernoff. And you can ask whether there is an HDX reasoning for this, or whether every distribution that gives you an HDX in this manner will satisfy Chernoff. So I will say first, this is not an empty question. First of all, if you have an HDX, you can also recover the distribution from it. So you can automatically get a lot of examples from this. But also, there are some distributions that to some people at least look more natural, which are coming from easing models from physics or matroids and so on, that also give you HDXs if you imagine them in this way. And you can imagine a lot of interesting distributions that actually give you these type of HDXs. And very broadly speaking, this is exactly what we showed. That if you take an HDX and you take all the hyperedges of size k, and you sample a point in your data space, not by independently sampling them, but by sampling them using an hyperedge, you can get the same Chernoff inequality. So I have maybe less than a minute to actually say something about this. I will just kind of say, this is maybe, you may think that, every HDX gives you something that's very statistically close to the independent distribution. This is very far from the case. You can think of things that are very far statistically, and yet you still have this very nice concentration holding. And I will also say that this also kind of comes up naturally in interesting questions and applications. Some, this hardness of approximation that I talked about, and also kind of things that come up in Boolean function analysis. And you can even kind of get extensions for these for functions that are more expressive than like empirical means on functions of vertices, which kind of also come up in questions of hardness of approximation. So maybe I'll just kind of conclude. So today I told you something about kind of the theory building you can expect in HDXs, and also something about the applications and where we can see these things actually helping us in theory. And there are many, directions of research and kind of different questions I can ask. I maybe just want to kind of end with asking this very broad question of like, which areas I don't know about personally, or maybe high-dimensional expanders can kind of help us solve major interesting problems. So thank you.
Question.